Welcome back to the Chemistry Lab. Today, we're taking our complex organic sources and distilling them down into a fascinating explainer on, well, molecular breakups and atomic rebounds. Specifically, we're going to unpack a comprehensive nucleophilic substitution unimolecular explanation with examples. It's literally one of the most fundamental and honestly dramatic pathways in all of organic chemistry. Let's get right into it.
So, let's kick things off with the most fundamental question we can ask about the chemical actors we're studying today. What exactly is an SN1 reaction? You know, to truly grasp the elegant mechanics of organic synthesis, we've got to understand the specific language and really the whole cast of characters involved in these microscopic interactions.
The name itself actually tells the story. SN1 stands for substitution nucleophilic unimolecular. Substitution just means we're swapping one part of a molecule for another, right? Simple enough. Nucleophilic refers to our attacker, our electron-rich hunter. And then there's that number 1. That is absolutely crucial, unimolecular. This means the speed or the rate-determining step of this entire molecular dance depends entirely on the concentration of just one single substrate molecule taking the leap. It's a total solo act that kicks off the whole shebang.
Here's our lab syllabus for today's explainer. We'll be looking at the art of the swap, the two-step breakup, carbocation stability, two-phased attacks, the protic solvent effect, and finally, some reaction examples.
All right, Section 1, the art of the swap. Let's meet the characters.
You know, organic chemistry mechanisms often look like a completely chaotic web of arrows scribbled on a chalkboard, but they actually just map out highly logical stories of electron flow. Every single curly arrow is literally just tracking the movement of a pair of electrons from a source to a destination. Once you learn to read the arrows, boom, the chaos completely disappears, and this beautifully structured narrative emerges.
To really get our narrative today, imagine you're looking into a beaker where a nucleophile, which we can think of as this electron-rich hunter, is seeking out a vulnerable, slightly positive carbon target. Haloalkanes make the absolute perfect prey here. Because halogens are electron-greedy, right? They pull electron density away from the carbon they're attached to, leaving that carbon with a slight positive charge. Our nucleophile, armed with a lone pair of electrons, is just waiting in the wings to pounce on that exact vulnerability. But how exactly does the hunter strike? Well, there are two main paths. Unlike the SN2 reaction, which is this simultaneous, crowded, kind of sneaky attack from behind that boots the halogen out in one swift move, our focus today, the SN1 pathway, is a far more dramatic, step-by-step molecular breakup. It takes patience. It actually requires the original molecule to completely fall apart before the new bond can ever be formed.
Moving on to Section 2, the two-step breakup. Let's see how the mechanism unfolds. This sequence brilliantly illustrates our two-step breakup. Step 1, the departing partner, which we call the leaving group, slowly packs its bags and leaves. This severs the carbon-halogen bond entirely, leaving behind a lonely, positively charged carbon atom, a carbocation. Now, this is the bottleneck, okay? It's the slow, rate-determining step we talked about earlier. But once that happens, Step 2 kicks in. Our hunter nucleophile swoops in incredibly fast for the rebound, attaching right to that carbocation. And sometimes, if our nucleophile happens to be a neutral molecule like water, there's a super quick third step, just to pluck off an extra proton, leaving us with a nice, stable final product.
Which brings us to Section 3, carbocation stability. It's all about speed and survival.
See, this reaction's speed completely depends on how well that lonely carbocation intermediate can survive on its own during that excruciatingly slow first step. If the carbocation is too unstable, the leaving group simply won't leave, and the SN1 reaction just won't happen. No way. So what actually makes a carbocation stable? Well, it's all about its neighbors. A tertiary carbocation, where the positively charged carbon is attached to 3 other carbon groups, is incredibly stable. Why? Because the surrounding alkyl groups essentially push their electron density toward the positive charge. It's an electronic life raft, known as the positive inductive effect. Secondary carbocations only have 2 neighbors to help out, so they're, moderately stable. And primary carbocations, with only 1 neighbor, they are highly unstable and practically never undergo SN1 reactions.
I absolutely love this quote directly from the source material because it hits the nail on the head regarding the reality of the lab. Secondary haloalkane molecules are like the annoying middle children of organic chemistry. They face a total identity crisis. They have just enough steric hindrance to block an SN2 attack, but just enough inductive stabilization to survive an SN1 pathway. Ultimately, they're torn between undergoing SN1 or SN2, and it depends entirely on the specific environment you put them in.
Section 4, two-phased attacks. Let's look at the stereochemistry.
When that leaving group departs in step 1, the carbon atom undergoes this wild geometrical transformation. The intermediate carbocation actually becomes sp2 hybridized. Visually, that means it's trigonal planar. Or in everyday terms, it is completely flat like a pancake. And because it's entirely flat, it leaves itself wide open to attack from both the front and the back. There's absolutely no structural block preventing the nucleophile from hitting either side.
And this two-phased attack means the stereochemistry of your starting molecule gets completely scrambled. Because the nucleophile attacks the flat carbocation equally from the left and the right, the result is what we call a racemic mixture. Literally, half of your newly formed molecules will retain their original 3D shape, and the other half will have an inverted shape. If you started with a pure single enantiomer, well, the SN1 reaction is going to destroy that purity, leaving you with a 50-50 mix.
All right, section 5, the protic solvent effect. Let's see who's controlling the rules. You have to remember, solvents aren't just empty space in a beaker, they actively participate. Protic solvents like water or ethanol contain hydrogen atoms attached to electronegative atoms. They act like this comforting, calming blanket, forming hydrogen bonds that surround and stabilize our vulnerable, positively charged carbocation intermediate. By lowering the energy required to form that intermediate, protic solvents effectively force the molecule down the SN1 pathway. On the flip side, aprotic solvents like acetone, they can't form those hydrogen bonds. They leave the nucleophile completely exposed and highly reactive, which heavily favors the sneaky SN2 simultaneous attack instead. Finally, section 6, reaction examples. Let's look at some real-world synthesis.
Imagine you drop some highly crowded tert-Butyl bromide into a beaker of water. The bulky structure of the tert-Butyl group completely, physically prevents the water from sneaking up and doing an SN2 attack from behind. It's just way too crowded in there. So the reaction is forced to wait. The bromine bond slowly breaks, the bromine leaves, and a very stable tertiary carbocation is formed. Then, boom, the water swoops in fast, attaches, loses a proton, and ultimately forms tert-Butyl alcohol. It's a textbook SN1 solvolysis reaction, dictated entirely by the physical structure of the starting material.
The rabbit hole of these mechanisms goes so deep. Beyond SN1 and SN2, there are even complex radical substitutions where single electrons are transferred to initiate the breakup. But honestly, no matter the path, the rules of electron flow remain a consistent, highly elegant language.
So, I want to leave you with this final thought as we wrap up this explainer. We just saw how merely swapping the liquid in a beaker from a product to product changes a molecule's entire structural destiny, shifting it from an SN2 collision to an SN1 step-by-step breakup. If the background liquid has that much immense power over the microscopic world, what other unseen environments are secretly controlling the reactions all around us? Keep questioning your environment and keep decoding those mechanisms.